All right. So welcome, everyone. Those of you into big data, we've actually got a very active big data community here in Los Angeles. I think we've got a couple of flyers in the back that you can actually take a picture of that will lead you to some of the big data meetups. We have big data meetups in the Santa Monica area, or Orange County, Pasadena, and whatnot. I know OpenX hosts Pasadena Big Data Users Group. So if you guys are at all interested in the big data stuff, talk to me, and I can kind of point you to some of the meetups. Again, you just go to meetup.com, search for big data, search for data science, search for data visualization, whatnot. We got a great community out there. And that said, here's Cody. He's going to present a little big data.
Hello. I'm Cody Ashe McNalley, and I'm a data scientist at UCLA and also collaborating with many other universities on sort of multi-site projects, which is kind of a key big data approach these days. But I sort of got into big data a little bit sideways. Like 10 years ago, I was doing sort of data warehousing and data mart. Actually, data mart. I was the consumer of like data warehousing information and created a product that created visualization and output and metrics before the big data term really took hold. And I like that, except for the reliance at that time. It was right out of college. I got a job as a consultant for big pharma companies, and the data was prescription data on specific companies' drugs and for the entire United States. And this could be mapped back to like particular doctors and things, particular doctors, zip codes, locations, and the pharmaceutical companies use this for sales and marketing purposes. I developed a product and took it to the point where like a team took over, but it was a little bit, this was sort of the beginning of concerns about big data, and eventually that same data provider, the data warehouse that I was producing the data mart off of, ended up before the Supreme Court over data privacy, and they won in 2011 on the current Supreme Court. So I went back to the academic setting and went back to Linux, which I had become a Debian user in college, and I built up servers, stood up servers at UCLA and USC, and really just enjoyed that. But I got pulled back into big data in a much better context with neuroimaging data, which is UCLA and USC are both very prominent in those and in that field. But in between that, I realized that it was not the big data that we talk about. I went to several of the big data talks earlier in the week, and the focus on sort of the 5 or 6 V's, depending on how you count it, it's a sort of a very narrow view of how this data processing, how machine learning, how streaming algorithms, how big I/O, how those are actually used in practice. And I've sort of seen this data strata, which, has anybody seen these before? Like, I know we all know big data, but the sort of other strata, it sounds like some people actually work in these other strata, but I'm really glad there aren't any. Are you guys all big data people, or just interested?
How do you define it?
Right. Well, that's exactly sort of what this talk is. The beginning of this talk is about, and then I'll talk about like how I implement it without worrying about the definition, which is ultimately what we want to do. There's, I think, a lot of pressure to sort of conform to particular technologies and workflows as being, the cool topics at. There's a Strata and Hadoop conference in San Jose. So I'm hoping that like all the people who are really, big on that are there. They did get Obama as the keynote speaker on video, and he had the chief data scientist for the United States there, and open government data is a great idea, and we are part of that. But again, at a slightly different scale, and I mean, big data has to start from somewhere. The millions of records that we have in databases, or the millions of files that we pull into any of the big data stores, they're aggregated from individual data sources, from nothing to start with. So let's see. The big versus small contrast. So it seems the big data community has realized that people don't know what big data means, and even more so, it isn't tangible. It's very abstract. So the way that this has become more accessible is to highlight the use value of it, which is individual metrics or refined data sets. And that is sort of what big data advocates call small data. And then there's another viewpoint, which is a sort of a contrast, which is the last article mentioned here, which is that a lot of times we're trying to shoehorn data sets into these big data workflows, or into even big data analytic methods that don't fit. So James Fogmoose, who's a computer scientist in Minnesota, I believe, he put out a blog entry on Medium, and there's a lot of, this was in October, there's a lot of data science and big data blogging right now. It has sort of, there's a lot of useful information, particularly on Medium, actually. But the idea is that, if you're not trying to sell something, then big data as it's construed by companies selling big data products is probably not going to be that useful to you. And the justification is, this is actually about neuroscience too. The example he gives is this sort of toast to crumbs, that if any data of any complexity, so if we go back to one of the V's is, of course, variety or variability, but the variety there is more single values, but just various values within a given metric, not the vast complexity of the data. So complexity is sometimes added on to the end of this, and by complexity, it's the idea is how many people click on a given link versus what every aspect of the page that they would look at, just as an example of that. Or medical scientific data is often extremely complicated due to the nature of, it's not a constrained system. Now let me see. So here we go. This was the first sort of big data analysis that we did at UCLA, my group did, and it's a recent article, but this really was sort of the perfect storm. We just pushed all our data through and, did the data curation as we went through, followed all the best practices, and through the efforts of all the authors listed there, we produced, this is a methods paper too, so we produced sort of the useful metrics that have come to be known as sort of big data metrics. Although this has the complexity element. There's very many different types of data that would go in. So according to the sort of Fogmoose view, this would be sort of an aggregation of smaller data as opposed to big data as it would be defined. So big data would be defined as a very homogeneous data set that you're looking for like precise predictors or parameters. So in a statistical sense, it would be large N, small p, whereas any kind of complex system would be large P, large number of parameters, large number of predictors that you're trying to estimate with statistics. Therefore, the N value needs to be comparable. You need a lot more N. Now, in terms of N, like in a data mart product or in any kind of data set that we have that we're capable of sort of interacting with, you might have hundreds of thousands, you might even have 1 million rows, but beyond that, the scale becomes difficult for a single computer to process. And that's sort of the difference between small data and medium data, is that this is, let me go one back here. That's that, okay. Sorry. This is the climate change is actually the Medium paper, the Medium blog post by Fogmoose. This is the article that he wrote in the Big Data, the journal Big Data, and climate change is another example of a data set that is often mentioned in big data contexts, but that really fails to be analyzable using the sort of simple workflows that programs like Hadoop and provide. The small data sets often have the same level of complexity. For instance, we want to use machine learning algorithms, classification. We want to use even like Hadoop. Often the simplest uses are things like pattern matching, word counts, grep, trying to find instances of keywords in large amounts of text data. These are sort of the hallmarks of like big data analysis now. And we can do that using Hadoop. I think one of the Hadoop examples is like grepping through, 100 gigabyte files, chunks that are partitioned out. But we also do that on the small scale, which is what I'm getting to with, this is a book by Jerome Janssens, who is the chief data scientist at Elsevier. And he sort of has the classic, like, Linux as an accessible interface for data for systems, just as Linux provided sort of an accessible entry to Unix for everyone who couldn't afford HPUX, AIX, Solaris, and in the same sense, it is now a platform that we can use for data analysis. I mean, it always has been. A lot of these, like GNU Scientific Library, GNU Plot, this book goes into, it has a lot of examples, a lot of custom code that defines like command line processing that is the same techniques that are used at the Hadoop level, but that you can do with a data set on a single computer. So if you have a 20 gigabyte file, like the standard GNU grep will handle it just fine in terms of almost any kind of pattern matching, log files, any kind of aggregated data. And let me see, we have at UCLA a number of big data groups that are doing sort of this kind of analysis, where this is actually by Tyson Condi. This was at the BD2K conference that we had. And the issue, of course, is the the modeling step, where, you know, this, once you can get Hadoop running, you have everything, you can able to bring your data in and bring it through. You still need this central step where the actual decision and classification, the statistics occur. And this is sort of the crux of this defines sort of the success of the entire process, and yet it's sort of this, it's stuck in the middle of the sort of map-reduce functionality. So by taking big data and returning to sort of a small data approach, you can curate the data and provide better data going in, and also validate and optimize your algorithm in the middle. Now, the interesting thing is like the MATLAB, R is often used for these as that sort of the central modeling algorithm, MATLAB too, but they're not mentioned in sort of the Hadoop world that much. It's sort of, that part is left to the statisticians or the data scientists who are working on it. And there's such a divide, like the O'Reilly books, there's the open source data analysis, or data analysis with open source tools. It talks about MATLAB, R. The Java section, though, it actually describes Java as being not particularly well suited for numerical analysis, because the Java numerics group like disbanded, and it's like too high level. Whereas you'll have like the big data books from O'Reilly will all be talking about Java-based workflows. You have this real division in specialties within big data. But the chief data officer of the U.S. at the Strata Hadoop conference, he came out with the first line was kind of the cheesy, big data is a team sport, which is kind of, I mean, I think they're trying to promote, you know, community-based or at least consumption of government data. But building that team is crucial, and the sort of small and medium data approaches, which are much more collaborative, have proven, will, I believe, prove very useful in the future. The particular project that I've been working on since that big data paper came out, we realized, you know, we want to be able to have a much better handle on our data. And by that I mean we want to know the validity, the veracity. We want to know the provenance. We want to have be able to think about it in an a priori sense, where we're able to do exploratory data analysis rather than sort of just pushing it through one of these pipelines. We put this together as a repository for data. It's called Pain Repository, Pain and Interoceptive Neuroimaging. Does anyone know what interoception is? So our senses are both external and internal to our body. And the internal pathways are different in many senses, in many contexts, than the external. So the sensations that we feel inside our body are interoception. And this is relevant in many medical conditions, because obviously they're internal and they're subjective in some cases, or at least our perception of them becomes subjective. So how do we gain an objective, clear insight into what is not externally sensible? The neuroimaging has become a prime possibility for this, because of the ability to, it's on the web browser, sorry. I do this at work too sometimes, and people don't like the switching back and forth too much, but I'll try. This is like stuck too. So this is Nature Reviews Neuroscience, and can neuroscience be integrated into the DSM-5, which is the Diagnostic and Statistical Manual for Mental Disorders, and it's been the hallmark of psychiatry for the last 40 years. And did anyone hear about this? It was in many media outlets, New York Times. There was a lot of discussion about this because the committee coming out with the 5th version basically postulated that neuroscience or some sort of advanced scientific method could replace common psychiatric practices such as subjective reporting. And the hope that neuroscience can do this is well-intentioned, and it will eventually satisfy the need to know more about what is going on inside our bodies. But it's difficult at the moment. So we're in this in-between phase between where classical medicine and science could make intuitive, reasoned decisions, and then where big data where data-driven diagnoses will happen. My portion of this, now I should say that in terms of, I'm not a statistician, my portion of this is much more systems-based, and from that regard, I'm much more interested in sort of like how to scale up these systems, but not the classical big data cluster where we run Hadoop only. This is actually from a group at UCI, which is very similar to our group, but it's a different group. And that sort of looking at the scales, this is Harry Mangalam's presentation on big data on Linux. How to scale, where is the point where big data becomes the proper approach? Now this, actually I'm not sure if this is 32 gigabytes and 64 gigabytes, but this is actually, all right, let me go to, here we go. The medium data set is a data set. This is Matt Hunt is Bloomberg's R&D. Medium data is sort of his focus, where it's too large to fit on any one machine, but it doesn't require this sort of cloud approach either. Now, if Bloomberg doesn't see itself needing this sort of big data approach, we need to sort of look at, like, how can we use smaller scale approaches to gain more accuracy? I mean, their issue is they actually have a daily runs of market information that they do run through a batch process in Hadoop, but so the data store from that has low latency, but the batch run is just once a day at the end of the day. Doesn't have the velocity aspect. Let me get to sort of here's where the complexity of the data comes in too. The Fogmoose sort of a critique of neuroscience as being, you're getting one set of data from the brain, and you can look at it any number of different ways, but you're also going to correlate it with any number of other metrics. And in terms of the kind of metrics that we get from our body, in terms of the genome, the brain is actually 20,000 genes are active in producing brain cells, 23,000 in the rest of the body. So the complexity of the brain is equal in some senses to the body. And then there's the new field of omics where you have microbiome. Does anyone know what microbiome is? It's like bacteria. So probiotics are sort of a current health trend in helping build up a better microbiome. It's the bacteria that live in our intestines. It's extremely diverse, and it defines like our everyday health in terms of digestion, mood. I mean, it has extensive implications. And then the further breakdown of that is the metabolomics, where you have like down to the protein and amino acid level. So the analysis of this is the classic like small n large p. Even if we scan 1,000 people, or 2,000, or 5,000, or 10,000, you're still not going to get the sort of classical statistic classifications of groups. You need to bring in, now we do, we can bring in classification, we can bring in the graph theory that's used in social networks. So we're actually using algorithms that are used for Facebook, but instead for the interactions of our mind and body. And there's a lot of data sets that are like this. One that I think goes back to the keynote Obama gave is they are sort of, Obama's known as this data president, and certainly he has promoted much more open government data and has assigned a chief data officer. The election, there was all this talk of big data analytics going into the election. And the complexity of any election is sort of one of these problems that probably doesn't fit big data analysis either. And sort of this is actually what this article in Pacific Standard was about, inconclusive results. Not only was the data set relatively small, I mean 15 terabytes, we have 8 terabyte drives now. We can fit, you know, two of these, 2 drives would have that without any redundancy. And that was incorporating 10,000 poll calls a night. So if you think about like your standard database architectures like MySQL, PostgreSQL, they can handle this scale just fine, and you're going to get the same, you're going to get all the tools that have been built up over 30 to 40 years since date and COD, and all the work that's gone into each of these. I actually think PostgreSQL is really probably an excellent big data platform because of the extensibility. You can, I mean, MySQL as well has built up because just the ubiquity of it. It has, you know, you can manage data in that and then feed into any number of other pipelines. Interestingly, in the scientific world, there's sort of like a do-it-yourself mentality where we actually designed. Has anyone ever used like the Sun Grid Engine or Son of Grid Engine? So there's these. This is a pipeline flow around SGE, and it's the same kind of workflows that we see now with like Juju, with, you know, the sort of big data ecosystem. But what this actually is a wrapper around shell scripts on an SGE cluster. So it's this group actually moved from UCLA to USC, and a lot of people used to like sort of quit using this after that. But it's a very nicely designed, 10 years of development. I use it to process basically the same workflows that you can do on the command line. Of course, you also, how many people are like command line oriented? Oh, great. So this is actually perfect in terms of the tools that we have available on the command line are, let's see. Oh, absolutely. Although I'm just, I will do that. this is actually, does anyone know, this is a brain model of, it's actually my daughter's brain. And this is an MRI scan that's been processed through a custom pipeline by Harvard MGH called FreeSurfer. And this is actually node-based graph of the brain that's then colored with there's visualization. Now, one thing in terms of if you have a data set with some complexity, the possible answers to getting better camera. No. Export. What we do here, and this can be done, I think, with any sort of spatio-temporal data. Anything where you have climate data, for instance, it's spatially related in the sense that the weather here is going to be similar to the weather in Pasadena. It's going to be, related. It's within a given small climate ecosystem, you're going to have the same weather. Here we've defined anatomical regions of similarity in the brain. This has been done from the entire history of neuroscience, has sort of coalesced into consensus views that these regions, these cells work together. Now, this is the same sort of representation of the brain, but with regions mapped out for particular cell groups. And this has been refined to the point where we actually can determine what parts of the brain correspond to given activities, given physiological processes too. Mood, anger, sensation, vision. This is actually a neurodebian. Debian has a neuroscience repository. It's for the last 10 years this has been developed, and it's extremely nice to work with. The servers actually use RHEL though, because I always feel like Debian is a user's operating system, and I haven't quite adjusted to Ubuntu as like the long-term support and the ability to, and there was a big transition 10 years ago from the old Unixes to Linux, and Red Hat sort of benefited from a lot of the sort of adoption of the old, they've done a lot of work on file systems to beef up the file systems for large workloads. The slide about the data size, Linux has come a long way, but the maturity of it as a platform for this kind of analysis has just started happening in the last few years. I think with the fourth extended file system, up until about a year ago, had a maximum partition size of something like 16 terabytes because the code was less than 32-bit mode due to concerns about what would happen if it switched to full 64-bit mode. I think it's up to 48-bit in the latest RHEL 7. But one thing I've noticed here at this scale too is that the RHEL 7 hasn't been. Has anyone gone to RHEL 7? So I've done it just in the last. It only has been out in the last 6 months, but I've started doing it in the last few months. But a lot of products, a lot of the sort of tie-ins, configuration management software is still catching up to it. For any kind of systems where, let's see what, so bridge between big data and small data, really any data, is always going to be like data, whatever term we want to use, data creation, data, we used to use scrubbing data. This article uses data janitor work. This is actually, I think, Fitbit, or is it Jawbone? And you know, the sort of Internet of Things, all these devices, these are classical big data scenarios. You're going to have very uniform data coming in, and there's going to be lots of it. So this seems surprising that they still spend a lot of time basically running through custom workflows on the command line, you know, cleaning up the data. They've devised the devices, they've defined the APIs, they're receiving the data from, it's a fairly closed ecosystem for them, and yet they're still trying to figure out, they're still spending 50 to 80% of their time on the same kind of workflow that you would with a data set that you weren't familiar with. Does anyone spend a lot of time like cleaning up data sets, getting it into systems, out of systems? I've spent I spend a lot of time doing this, and it's actually very satisfying to sort of take a data set and get it from some kind of, you know, messy state into something that can be combined and used for a positive outcome. One of these, so along with big data, I wanted to make the contrast, big software versus small software. Now, big software is actually a term that used to be around. I think big data sort of like confused the issues. But little software, these are things like GNU utilities. I mean, these are things where everyone who's used Linux for any period of time, we know these utilities pretty well. We never know these utilities as well as we could. There's the bash man page is such a well-written tome. It's like has anyone read the bash man page? I mean, it's amazing that has all been one developer essentially for the past 20 years, and then I think it was, you know, one developer, Brian Fox, handed it off, and the level of complexity in bash, I think there's sort of bash bashing where people view bash as just you know, here's my entry point to my, you know, I'm just going to run my Python, my whatever programs they use, even like the Hadoop, you can launch like all your Java jars from the command line. But the approach that's presented in sort of this approach is, it's quite it's both entertaining to see an ASCII histogram, and it turns out to be fairly useful. I mean, instead of a lot of the issues we have are, you'll receive data sets where some nodes in the data set are empty. Some directories end up being empty. Didn't transfer. The data was incompletely collected to begin with, and without the metadata associated with that, you have to sort of use this approach where you're doing exploratory data analysis of the data as a data set, not even to the point of what the data contains and what it represents. Now the particular data I work with, like imaging data of any kind, I think is sort of like the next stage of, you know, they've been working on image-based search. That's pretty well established, at least sort of facial recognition, which seems like not the most useful application of that level, the level of complexity that's gone into it, but for both social and surveillance reasons, these are sort of open source libraries that are associated with DICOM, which is Digital Imaging and Communications in Medicine. This has been sort of like my lifeline into these systems. It provides open standards that have been adopted across the industry, and by pulling all of the information out, we can combine data in any number of ways using all the information. Let me see if I can, this has got, whoops, thought I had that here. This one. So we can pull out any kind of information from the data in this repository. Now, this is actually my key point too, is that when we have data in repositories, whether it's, it's a relational database, just as flat data store, HDFS, the need to sort of do exploratory data analysis, it cannot be underemphasized. I think we lose a lot of data in workflows or in our work where we're trying to get to some answer. But there might be many different answers to many different questions in our data that we do not explore because it doesn't produce the final metric that our product has, or our query has asked. And that's where sort of a different technical approach comes in. Right now, at this time, I assume you chose this talk because you're interested in data rather than systems, but there's 2 storage talks going on. Both are now Red Hat products. There's GlusterFS, there's Ceph, and there have been a number of talks on OpenStack, on private clouds, on products like that. And then in terms of software, in terms of what software we're using to analyze the data in our data stores, we have these low-level utilities. You have the GNU utilities. You have small custom-written. I've written a bunch of C and C++ wrappers around the DICOM libraries to pull out information. We've written APIs on the database to store all the information from the images. When we approach the big data world, there's the base distributions break down a bit. I don't know if anyone's built up like any systems using sort of like the Apache ecosystem of big data programs, or any of the other analytical packages, even something like SAS. Like I've spent like days trying to install SAS. I spent much of last week trying to install a Python-based metabolomic analysis toolkit that had updated for the first time since 2013. They came out with an update, and that interdependencies of the Python libraries really could not be solved very easily. Most of the time now we need these we need a distribution of the particular tools that we're using. There's the Apache BigTop, which is sort of just coming out. It packages all of the different Apache big data programs. For Python, there's Anaconda Python. It's sort of like apt-get for Python, but I guess also that would have been pip and easy install and all of these. And then R, for being that critical central element, the criticism that R is hard to scale, it's still not really entirely multi-threaded or not able to process in parallel. So this company, Revolution R, they took the open source R code, cleaned up the threading support, and produced a really nicely packaged jar, and then Microsoft bought them. So this is definitely where the big data is headed. Now, if you're able to work on the command line, that Jerome Jensen's with the command line data set analysis on the command line, I saw he's actually in London giving a workshop on that, on the topics of the book this weekend. But he had a webcast a couple months ago, and he's like, yeah, I don't even write R well enough to use it on a daily basis. But as part of a team, you know, a statistician will help write a module, and that can be just called on the command line. Now, that can be called just as easily, and R can scale just as well, especially if you use sort of this is open source as well, it's still. You can, within a given system, let's see if I can, there's something here super. Does anyone do hardware? No hardware people?
Well, what do you mean by that?
Do you design, when you design systems, do you have to architect the hardware?
So set up servers, set up networking.
Okay. So, I thought I had a slide for this, but so this kind of system now this is like if you went to the Gluster talk, Red Hat actually, because they're selling per server licenses for storage, and having gone to a number of talks on Gluster and Ceph over the last few years, it's a really ideal approach to data because you have block access, you have object storage access, the granularity is the performance is really good, but the licensing is very valuable because if you try to put these systems together yourself, it's totally doable, but there are many caveats that Red Hat has gone to a great deal of trouble to, and Inktank as well, to fine tune. They'll know when you can ignore a warning versus when you can't. Whereas if you're putting this together yourself, the number of warnings and the number of situations where the system can become unresponsive is surprising. The UCI group actually migrated from Gluster to Fraunhofer, which is now called like BGFS, with some of it was like a live 500 terabyte storage cluster that they migrated, which is really impressive. So with these systems, if you have, say, 40 drives or 36 drives at 8 terabytes each, you're looking at, like, what, 280, 36 times, 288 terabytes on one system. Now that combined with a quad Xeon system has about the application power of like any cluster that was designed like within the last 10 years. It doesn't have the scalability of the cloud approach where you can go to the n equals 100, 200, 300, but for it's sort of the perfect medium data approach, and it's sort of the solution that Red Hat is focusing on for their storage options. Just so you can know, does anyone have like a particular data field that they're coming from that they find doesn't fit the big data approach? No? So how many people work with data?
Well, I support a lot of research scientists, right? So, but they're using MATLAB and Octave and R and those types of tools. The data that they're collecting is experimental and not in the health field. So they're not like, you know, the world observation. I mean, they may run an experiment and get 50 or 70 gigabytes of image data.
Right.
High-speed cameras and that kind of stuff. But they use
Right, right. I think
But
this
they're
is,
not using like MapReduce, that kind of stuff is irrelevant.
right. Well, this book, he actually goes into GNU Parallel,
Yes.
which I've been trying to use that. I mean, I've used it for years, but like the Red Hat version is really, the EPEL repository version is really out of date, and it doesn't have like all the options. And I mean, this is really where you know, Docker or your Vagrant could come in, where you can bring up an environment. I actually used for the Python problem the other day, I actually used Red Hat's what is it, the SCaLE, the software collections. It was sort of like, it's sort of like a lot of shell manipulation to define an environment in which you can run different versions of Python, and they all play nicely. I mean, that kind of approach, when I saw it last year, I'm like, I don't know how it's like not a container, it's just, it's your shell, you're redefining your shell as for a different version of a core operating system library, and it worked beautifully. It worked better than the Docker or the VM approach, although the VM, there was something, I don't know how often you guys had this with, we use Vagrant a lot for, oh, okay. So this, for instance, there's a Vagrant box for this book, and you can tell that this is not big data though, because there's no Docker instance for this book. So I have worked with this great team of people. It's a group of clinicians, statisticians, physicists, and I think one of the things that I'm really lucky to work with this team who, this is going to play? I don't know. No. Work with a team of database administrators to find a way to work with other specialties. So they're not interested, unfortunately, in Linux, or in storage per se, but that's okay because I love those things. And I can, when I do need help, they're willing to pitch in, and it's like a visualization of software development. But I mean, I think we can all see if the difference between small software and big software in terms of how we put that together. The big software is going to require an approach. Like this is actually a really promising looking approach to big data, is that you can just bring this up on an individual machine. And Konstantin Budnik, who ran the big data workshop on Thursday, he really, he was working with the development like, oh, this Hiera code just came in last week. We got it working, even though it's like that cutting edge. So within the next few years, where we're able to bring big data down to the small data space and bring the small data approach of really exploratory data analysis, a priori hypotheses that we can bring into the big data space, so it's data-driven, but also hypothesis-driven. These are really going to make all of these strata work together. And I don't know what we'll call it then. We'll just call it data again. That'll be nice. But does anyone have any questions?
Any questions? Raise your hands. I'll bring the mic to you.
One question. Can you go back to this slide where you have some data from the CI, the one that shows the different?
Oh, sure. I can.
My question basically regards to the human genome, which is, I guess I saw that at about 3 gigabytes per person, which to me, based on what you're saying, if we can just do some kind of machine learning on the data, we can probably do lots of good thing about finding the cause of many diseases or something like that.
Oh yeah, absolutely. The interesting thing is that data-driven approaches to genetics, it's sort of you end up with a many-to-many issue. The number of parameters, the number of connections, the number of interactions in the genome are so far extremely complex. They're beyond the sort of a simple data-driven approach. If you push all your like GWAS data, genome-wide association studies, if you push that all through a big data pipeline, you'll get kind of random results. that won't make any sense. And this goes back to sort of the small data masking it as big data. Even if you have, how many genomes, people's genomes do you have to push through? That variability, so how many thousands do you have? It still might not be enough to truly separate out different classifications using that kind of statistical approach. And then so what you're finding is kind of anomalies, but you might not know what those mean. And without an idea ahead of time of what you're looking for, or even if you do, say you're looking at Alzheimer's or schizophrenia or any of these, you really have, and the truly brilliant geneticists at UCLA and USC, these talks I've gone to, they really struggle with this. They're like, well, we need to keep pursuing this, but the approach of just analyzing that, which is even if you aggregate, 1,000 of those, it's not enough data. And this is where big data really becomes interesting, is that there's this sort of like threshold where these classification algorithms work really well, and we need to come up with an approach where that will work at a smaller scale. And it involves just new methods and and also much cleaner data. So to give you an example from, anybody else have any questions? Oh, this one? Oh, Harry Mangolum will be so happy that he got 2. He is a data scientist at UCI who I always comb through. He has like the classic Unix guru directory full of all of his presentations. And, we don't put those out there because we don't want people to see our typos as much. But he's just like, here it is. And I go through those all the time, and I find, and it was actually reassuring to know, like, well, they're still struggling with what approaches to suggest. I'll put the URL up in the works cited on the presentation, which will be on SCaLE's website. Are you going to be emailing that to us, or? Yes. Okay. So right now, I guess you can search off of UCI. And UCI has a lot of big data. They're sort of a big data center for the world. They have repositories of a lot of the data sets that are used as testing data sets for these algorithms. I don't know if you'd find this, I guess, big data on Linux data science, but it's pretty buried.
So a question on going past the threshold. Right now, you're dealing with large-scale databases. You're starting to have performance issues. You're looking at the same data sets all the time. In my case, we were looking at fraud data.
At what data?
Fraud.
Oh, fraud.
Fraud detection.
Yeah.
And those types of things, or security breaches or whatnot, looking for anomalies and whatnot. At what point do you consider a threshold when you start getting massive problems with the database, when you bursting, for instance, if you get a whole bunch of data all at once, like collateral data during sign-up promotions or whatnot. So that's what part of what I wanted to see in your talk.
Oh, sure. So scaling in terms of throughput, that, I haven't had any performance issues, and but our data is, it actually is surprisingly even in how we receive it throughout. There aren't any huge, but I completely understand that certain types of data will come in these huge batches. I would think just optimizing. See, the thing is, you write your tools for the sort of pace of data that you're normally working with, and then all of a sudden there'll be this tremendous burst of data, and the tools will sort of break down at that method. So I think it's optimizing the tools is probably the trick. There's somebody had a talk this weekend, and I think it was Brendan Gregg, and he's like, if you have performance issues, you're probably, there's something there that you can do to fix that.
Well, what's kind of sad is, like, when it was a homegrown solution for us, we had multiple file servers that dumped all the syslog data into one area for us to actually put everything. And you could get a lot of data back by doing multiple grep's across. And we just had our tools that would just run grep all across and collate onto another another network drive afterwards, and results would come fast, especially when you're dealing with a cluster of multiple hundreds of web searches. But then we started looking into things like Snort and whatnot, to make search is easier, more interactive, but then we run into performance issues, and of course, Snort is expensive when you start going into the large scale loss. So,
Yeah, so you're looking at streaming stuff then? Streaming data. It's like live data is coming in. So there's a lot of interesting talks that have been covered on that, and in different venues and whatnot. One of those venues is the Spark meetup, that's associated with our Big Data LA user group. So you want to check that out. And I want to right now give a big thanks to Cody because we're kind of run out of time. And just let you know, also we're going to do a big data day in June 27th. So we'll probably cover some issues like that. We're still working on the venue, but go to the Big Data Users Group on meetup.com. Okay. Thank you very much, Cody.
Thank you.